Ok, Andrea, se vuoi iniziamo?
Va bene, thanks.
Ok, thanks to you. Ok, dear colleague, good afternoon. Welcome back to the webinar series on nonlinear differential problems organized in the context of the project PRIM nonlinear differential problems via variational, topological, and set-word methods. Project supported by the Ministry of Education and Research of Italy. This afternoon, the distinguished lecture will be delivered by Professor Andrea Cianchi from the University of Florence, and the short talk will be presented by Whit Musil, a PhD student of the Masaryk University of Brno, Czech Republic. On the behalf of the organizer, let me thank a lot Professor Cianchi and Dr. Musil for accepting our invitation to give a talk in this event. Talks that sure will reach the scientific level of the webinar. Many thanks also to all of you for your welcome participation. Professor Cianchi, as many of us know, is a very high-level mathematician, and therefore there would be no need for further work to introduce his talk. However, I wish to recall here only some main points that characterize his intense and deep research activity in mathematics. Professor Cianchi was a principal investigator in many Italian and European projects. He also received many awards and honors, as the Postgraduate Research Prize of Fondazione Francesco Saveri, the prize Gaetano Fichera awarded by the Italian Mathematical Union, the prize Luigi e Wanda Merio, awarded by Istituto Lombardo delle Scienze delle Lettere. He received also the commemorative medal of the Faculty of Mathematics and Physics of Charles University in Prague, where he is a permanent guest professor since December 2014. He was also plenary speaker at the 19th meeting of Italian Union Mathematical Union and invited speaker to Indam Day some years ago. This afternoon, Professor Cianchi will speak about a very interesting and fruitful topics. Fractional Orlicz-Sobolev space. Please, Professor.
Thanks a lot, Pasquale, for this introduction. I wouldn't deserve it, but thanks anyway. And thanks to all the organizers for their kind invitation to deliver this talk, which will deal with some recent work with Andrea Alberico, Lubos Pik, and Denka Slavikova concerning some extension of the theory of fractional order Sobolev spaces to the framework of Orlicz spaces. Here are the papers on which my talk will be based. I'm not sure whether I'll be able to report on all this material, but let me start by the main topic in this connection, which deals with embeddings, in particular embeddings of Sobolev type. So before going into the specific matter that we dealt with, let me recall you some more classical facts about, first of all, the theory of standard Sobolev spaces and then integer order Orlicz-Sobolev spaces. So just to fix some notation, I denote by W1P the space of weakly differentiable functions which are in LP and whose gradient is also in LP. So this is a classical Sobolev space. And by V1P, I denote the space of function whose gradient only belongs to LP. Here, omega is an open set in Rn, but for the most part of my talk, I will be dealing with the case when omega is the whole of Rn. Now, when one deals with Orlicz spaces, this means that the role of the Lebesgue space LP in the definition of these spaces is replaced by a more general Orlicz space, which I denote by LA. And in these spaces, heuristically, the role of the power t to the p is replaced by a more general Young function, a. This means that a is a function from 0 infinity into 0 infinity, such that it is convex and vanishes at the origin. Now, maybe most of you are familiar with these Orlicz spaces, but let me just recall that the norm here, it's usually considered as the Luxembourg norm and is defined in the following way. One has to be careful because I mean, if one considers only the space of functions for which a of u is integrable, then this is not a linear space in general. So one has to be more careful, and the space is a set of all functions for which there is a lambda for which this integral is finite, and the norm can be defined as follows in this way. Now, given this Orlicz norm, then the Orlicz-Sobolev space is defined similarly as before, requiring that u and the gradient belong to this Orlicz space LA. So typically A, apart from powers, can be a function that grows like an exponential near infinity, or like a power time a log near infinity, or variants of this. I'll give you a few examples later. And the homogeneous version of this Orlicz-Sobolev space is defined as the class of functions whose gradient is in LA. Now, this kind of spaces arises in a natural way when one deals with, for instance, nonlinear elliptic PDEs or problems in the calculus variations, where the growth of the coefficients is not necessarily of power type. But the study of these function spaces is of its own interest because I mean, their study sheds some new light in the standard theory because it has some special features that permit to unify this theory in a more suitable way. And the study of solid embeddings gives an idea of the situation at hand. For instance, it turns out that the class of Lebesgue spaces, Lebesgue norms, is not sufficiently wide to be closed under the operation of associating an optimal target in a Sobolev type embedding. What do I mean by this? Now, assume that omega is, for instance, just a regular bounded open set in Rn, then it's well known that the space W1P is continuously embedded into this Ln p over n minus p Lebesgue space if p is less than n. It is embedded into L infinity if p is strictly larger than dimension n, and it's embedded in LQ for any finite q in the borderline case when p equals n. So it turns out that no optimal Lebesgue space exists for this borderline case when p equals n. If one enlarges a class of admissible norms to include all Orlicz norms, then this problem doesn't arise. So a general result in this connection tells us the following. So you start with a Young function A, as in the definition I gave before, and one considers this Orlicz-Sobolev space W1A. Then it turns out that there always exists an Orlicz space, which I denote by LA sub n, for which this embedding holds, and for which this target space is best possible in the sense that it's the smallest possible among all Orlicz target spaces. And this function A sub n can be given an explicit form and is the following. So you start with A, you build up this function h sub n by this integral. Then this optimal kind of Sobolev conjugate of A sub n, is a composition of A with the inverse of h. This goes back to some old papers of mine, some 25 years ago. And let me point out that in these formulas and in other formulas that we will see later, one should not be afraid of these integrations that appear and inverses that have to be taken, because in practice it's not really necessary to have an explicit expression for H or for its inverse. What is only important in the definition of these ordered spaces is the asymptotic behavior of this function A sub n. And this can be easily determined for concrete choices of the function A for the integral and for the inverse. Now, this is stated for this space W1A, but there are analogous versions for the space of functions that vanish on the boundary and for the space of functions that are defined in all over n. Now, if one applies this result to the special case of W1P, so you start with the standard Sobolev space, which means that A of t is t to the p, then one recovers these embeddings for p less than n and for p larger than n I've shown you before. But in the borderline situation, one gets this exponential type space, which means that e to the u to the n prime, when n prime is the conjugate, is integrable over omega for some lambda in the definition of the norm. And all these targets are optimal, not only among the vector spaces here and there, but in the larger class of all Orlicz spaces. So in particular, for P different from N, as I said, this recovered the classical Sobolev embedding, and in the borderline case, one finds this Bozyv-Chulinge-Yudovich type embedding, which is well known. And this, as I said, gives optimal information about the target spaces as well. Now let's move to the main topic of today's talk, which is fractional ordered spaces. So if one goes to fractional integration, then, differentiation, then there are several notions available in the literature, and they include the classes of Biezov, Lidzorkin-Tribel, Bessel potential type spaces, for instance. The notion that I'm going to use is based on the definition of Gagliardo and Slobodevsky type semi-norms. So again, let me start by recalling that the study of these spaces has been a new interest starting from the early years of this century, especially thanks to the work of authors like Bourgain, Brezis, Caffarelli, who did a lot of work on this, and also Vladimir Mazia. Now, in the classical setting, where only power type functions are allowed, given an exponent S, S will be the exponent that governs the smoothness of the functions involved, and the power P larger than or equal to 1, then this semi-norm is defined as follows. So this is quite standard, is a double integral, which involves a kind of difference quotient of the function u, and it's not the standard one, but instead of power 1 in the denominator, there is an s. The form that I use here is slightly different from the, I mean, it's equivalent, but it's written in a slightly different form from usual, where you see just power sp plus n in the denominator. But I prefer to write it in this way in order to emphasize a similarity and analogy when I will move to the Orlicz setting. And now the space VSP, which is a homogeneous fractional space in Rn, is then defined as a class of functions U for which this semi-norm is finite. Now, for this fractional Sobolev spaces, there is a classical embedding, which tells that if P is larger than 1 and smaller than this critical exponent n over s, in the first order case, we had here just n. Here we have n over s. Now, under this assumption, then there exists a constant c such that this semi-norm dominates this Lebesgue norm of U. where now the Sobolev exponent is np over n minus sp. And now, since here we have just a semi-norm, we need some normalization for our trial functions. And if we work in Rn, one can just assume that u decays to 0 at infinity. Of course, compactly supported functions are admissible, but I'll give you in a minute a definition which is weaker in a sense, and the weakest possible for which this kind of inequalities holds. Now, let me also point out that even if you set S equal to 1 in the definition of these fractional spaces, you don't recover the definition of the first order B1P. So this is what I mean by this non-equality. Yet the Sobolev exponent that you have here with S equal 1 gives you back exactly np over n minus p, which is exactly the Sobolev exponent for the standard first order Sobolev embedding. Now, what about fractional orders Orlicz-Sobolev spaces? Now, this can be defined in a natural way, replacing the power p that appeared here before in this difference quotient, or S-order difference quotient, by this more general Young function A, so by this convex function A. And as in the standard case, when you define norms in this Orlicz spaces, one has to use this kind of Luxembourg type norm. So take the infimum of all lambdas such that this double integral does not exceed 1. Now, with this definition in force, then I denote by VSA the homogeneous fractional orders Orlicz-Sobolev space for which this semi-norm is finite. And by functions that decay to 0 near infinity, we can allow all functions such that the level sets of the absolute value of u larger than t has finite measure for all t larger than 0. So of course, if the function has compact support, this is true, but this allows for much more general functions in these spaces. And the class of functions that satisfy this condition, I will denote by VSAD. This stands for decaying. Now, the question is of finding some optimal, possibly embedding for this kind of space with targets which lie in a class of Banach function spaces. So this should extend and reproduce the classic embedding, the classical fractional embedding I've been shown to you a few minutes ago. Now let's start by considering embeddings into target spaces that are also of Orlicz type. So it turns out that like in the first order case, in the integer order that I've recalled to you, there always exists an optimal Orlicz target space for these spaces VSAD in Rn. And the construction is as follows. So we start with the function A in the definition of these spaces, which has the following properties. First of all, we require that this integral at infinity is divergent. So this means that A does not grow too fast near infinity, in a sense. I'll comment on this in a minute. Second assumption is that vice versa, the integral at 0 of this ratio is finite. Now, this assumption 3, this divergence at infinity, it's the analog of requiring that A has a non-supercritical growth at infinity. So, for instance, if A of t is this power t to the p, which gives us back the classical situation, then assumption 3 is satisfied if and only if P lies between 1 and this critical power n over s. Notice that n over s is allowed. So the critical growth, critical in the sense of Lebesgue spaces, is included here. Now, with function a, with satisfying this condition, one constructs functions h and a sub n over s in a similar fashion as before. So this function h is defined by this integral, and the associated function Sobolev conjugate, the fractional Sobolev conjugate, is defined as a composition of a with the inverse of h. And then it turns out that this function here gives us the optimal fractional Sobolev conjugate of a. And if you set s equal to 1 in this definition, one reproduces exactly the function a sub n, which appears in the optimal integer order Orlicz-Sobolev embedding. So the result, the first result of ours, is the following. So we start with the parameter s, smoothness parameter s between 0 and 1, and a Young function which satisfies these conditions. Then this fractional order Orlicz-Sobolev space is continuously embedded into this Orlicz space associated with this function a sub n over s, and a Sobolev type inequality holds for all functions in this space, which decay to 0 near infinity. And the point is that this is best possible because this target space here is the smallest possible among all possible Orlicz target spaces which are allowed. Now, concerning these first assumptions I've already commented, this subcritical growth near infinity, the second assumption is necessary in the sense that no embedding of this form, so from this fractional space into an Orlicz space, can be true if this condition is violated. So this is inevitable. Now let me show you some example. So first of all, if we go back to the case when a of t behaves like t to the p near infinity, so that we are back to the classical fractional spaces and p is less than or equal to n over s, then this embedding tells us that this space here is just a Lebesgue space with this exponent if p is subcritical, and is this exponential space if the p is critical. And this is optimal for every p in this range. And in particular, this recovers this classical fractional Sobolev embedding, and in the borderline case, this yields a kind of Poiseuille-Trüdinger-Udoggi type result. Now let's go to a non-power type example, which is just a perturbation of a power. So a of t grows like t to the p times some power of a log. And so these powers p and alpha are related as follows. If p is 1, then since this has to be a convex function near infinity, then alpha has to be non-negative. If p is between 1 and n over s, then alpha can be any real number. If p is critical, then alpha is less than or equal to n over s minus 1. This restriction comes from the subcriticality growth near infinity. So the condition that tells us that that integral of near infinity has to be divergent. Now, under these assumptions, we have this embedding where this Sobolev conjugate has these behaviors. So if p is less than critical, then it's a power time a power of a log, which depends on alpha, p, and s. If p is critical, but alpha is subcritical, then we have an exponential type growth of a n over s. And if both the power of the function and the power of the log are critical, so both of them are borderline, then we have this double exponential growth near infinity. So very fast growth, which means very strong integrability of the function u. And in all these cases, this Orlicz space is optimal. Now, in particular, in these critical cases, this gives us fractional versions of some old embeddings which are due to Fusco-Lyon-Bordone and Edmonds-Kurka and Opitz in the integer order case, or in cases which also include fractional spaces, but in a different spirit, the one of Bessel potential spaces. Now, these embeddings, which are already optimal as far as Orlicz targets are concerned, can still be improved if one enlarges the class of target spaces. And enlarge means that now one can allow for any target space which is a rearrangement invariant space. So what is the idea here? So back to the classical fractional Sobolev spaces, where here we have a power p. It's known that if p is smaller than n over s, then in fact this embedding holds, where in the target we have this space L with two exponents. The first one is as before, the second one is p. So this space is in the class of Lorentz spaces. This theorem is due to Rupert Frank and Seringer. And so again, maybe most of you are familiar with Lorentz spaces as well, but let me just recall a definition in this special case, which means with these two special exponents. The norm in this Lorentz space is defined by this formula, where LP is the backspace, and this U sharp, U star, denotes the decreasing rearrangement of U. So this norm is defined as the norm of the decreasing rearrangement times this power of R. And this is really an improvement of the classical embedding, because this Lorentz space is strictly smaller than the Lebesgue space associated with the first exponent appearing here. And the reason is that the second exponent is strictly smaller than the first one. So this is actually an improvement of the classical fractional Sobolev embedding. Now, we were looking for an improvement of this first result I've shown to you in the same spirit for this Orlicz-Sobolev embeddings. And in fact, we look for the optimal target here, which is optimal in the target of all rearrangement invariant spaces. Now, I'm not going to give a full definition of these spaces. What is important is that these are Banach function spaces, such that the norms of two functions are the same if their rearrangements are the same. Now, again, I'm not going to define rearrangements. Most of you are familiar with this definition. Let me just say that the two functions have the same rearrangements if their level sets have the same measures. So in a sense, these rearrangement invariant spaces have norms which are invariant under replacements of a function by another function whose level sets have the same measures. Now, what about the statement of this result? Again, one starts with the fractional Smoothen exponent S and a Young function as above, that now I represent in this form, since capital A is a convex function vanished at the origin. This can always be represented as an integral between 0 and t of an increasing function a, small a. Now, given this representation, one builds up another function a hat, again given by an integral of an increasing function lowercase a hat. And this lowercase a hat is defined through its inverse by this formula. This formula is quite scary, but as I said, since only the asymptotic behavior near infinity is important, near infinity or near 0 or both, then this can be computed in concrete situations. So the behavior of a hat can be found. Now, let me point out that in general, a hat grows less than the original a, so it's dominated in the sense of Young functions, and they are in fact equivalent in most cases. Most cases means that the original a grows less than the critical power t to the n over s. Now, grows less can be made precise in terms of what are called the Matuszewska-Orlicz index of a, and this has to be strictly less than n over s. Here there is a definition, but I don't want to insist on this. Let me just point out that if a of t is a power, t to the p, then if p is strictly less than n over s, then a hat is equivalent to t to the p. So it's equivalent to the original function a. But if a of t is t to the n over s, then a hat is actually growing slightly less than a of t. It's not t to the n over s, but it's t over log to that power. So it can actually grow a little more slowly than a. Now, with this definition a hat at disposal, one can define in a similar fashion as the Lorentz spaces what we call an Orlicz-Lorentz space. And the definition of this norm is similar to the previous one. You remember before we had this power, same power r to the n minus n over s, time the decreasing rearrangement of u, and the norm was taken in LP. Now, we cannot take the norm in the original LA. What is important is that the norm is taken in this space LA hat, which, because of this relation, can actually be slightly weaker than the original one. Now, with this definition in place, I can give you this formulation of the theorem. And this tells us the following. You are given a fractional exponent between 0 and 1, and function a and a hat defined as before. Then this fractional Orlicz-Sobolev space is embedded into this Orlicz-Lorentz space. And a Sobolev type inequality holds between this semi-norm and the norm. And now this space here is optimal among all rearranged invariant target spaces. Now, let me check the timing. I won't have time to go through even a sketch of the proof. Maybe I jump to the last part, but let me just tell you that this result about Orlicz target is deduced from the second theorem I've shown to you, which is the one about the optimal Ri target. And this second result, this theorem number 2, is obtained as a consequence of a Hardy type inequality for functions in this space. Now, what I mean by Hardy type inequality? Again, just to put the result in perspective, let me recall you that the classical Hardy inequality in Rn tells us that if p is strictly less than dimension n, then this norm of the gradient of a function u in LP dominates the LP norm of u over the power then the norm of x. And this is true for all functions u that decay to 0 near infinity in the sense I've specified before, and that have gradient in LP. Now, a fractional version of this inequality was proved by Vladimir Mazia and Tatiana Shaposhnikova in their paper about fractional embeddings, and they show that this fractional norm with p less than the critical exponent n over s dominates a similar expression where in the denominator, instead of norm of x, you have norm of x to the power s. Now, one of our results tells us that a similar inequality holds in this Orlicz setting, and the ingredients are as before. Exponent s is between 0 and 1, a and a hat are as before, and then one has this Hardy type inequality with the same structure, save that again on the right hand side one starts with a, but on the left hand side one has a hat, and this a hat can actually grow slightly less than a near infinity. An integral form of this inequality also holds, and has this form where on the right hand side one has this double integral of the difference quotients of u, and on the left hand side there is this integral of a hat of u over x to the s. Just an example, let me take a of t as before, which grows like t to the p times log t to the alpha near infinity. Then this Hardy type inequality holds where a hat is the same Young function as on the right hand side when p is subcritical, so if p is less than n over s. If p is critical but alpha is subcritical in the sense as before, less than n over s minus 1, then there is still the same power times a power of a log, but you see the power of a log is smaller. It's not alpha, it's alpha minus something, minus n over s. And in the double critical case, where p is n over s and alpha is n over s minus 1, then this the original power t to the n over s is multiplied by a negative log times a negative log log. So there is another loss in the growth of a near infinity. Now let me skip, maybe I have 5 more minutes. Let me just tell you that additional results are proved in our papers. For instance, we can deal with higher order fractional Orlicz-Sobolev spaces, which means that these are function spaces where instead of requiring that this fractional norm of u belongs to the Orlicz has this double integral finite, one can require that the functions have integer order derivatives up to some order, and then the fractional part of this highest order derivatives belongs to this fractional Orlicz-Sobolev space. Yeah? So for instance, spaces order 5 over 2, just to say. And one has similar embeddings into Orlicz spaces or into rearranging invariant spaces. Then we have results which hold in domains instead of the all over n. And these domains are bounded sets which satisfy some regularity assumptions on the boundary, and for which, again, we have similar embeddings and the results. And finally, we can characterize compact embeddings, which means conditions on the target spaces under which these embeddings are not only continuous but also compact. And this is, of course, of interest in applications, for instance, in the study of long local problems that are quite fashionable, which may involve fractional Laplacians of Orlicz type. There are already some papers appearing in the literature where these kind of questions are considered and make use of these compact embeddings that we dealt with. So I'm afraid I don't have time to go through the other issues that we were considering in our papers, which deal with the limits of this spaces when the smoothness parameter S goes to 0 and to 1. These were considered by these authors like Bourgain, Brzezinski, Mironescu, and Mazia and Shaposhnikova in the early 20s. In the classical case, we have versions of these results for Orlicz spaces, but I mean, if you are interested, I can send you exact references for these results. So I think that it's a good time for me to stop here, and I just thank you for your kind attention.
Thank you. Thank you very much.
Thanks.
For your interesting talk. There are questions, comments, remarks. Sorry, just a curiosity.
Yes.
We work with a more general space, more general operator. I think that this helps us to find with a more general class of nonlinearity respect to the classical Sobolev space, or no?
Yes, you mean if you deal with, for instance, in the integer order.
Yes.
Instead of having P Laplacian type operators, one deals with operators where one has some, let's say, the corresponding result would be the derivative of a convex function, of a Young function, evaluated at the norm of a gradient of u times gradient of u and divergence. So this is the analog of the P Laplacian in this Orlicz setting. Yes. And this kind of equations have been studied quite a lot in the literature, and the integer order Orlicz-Sobolev spaces are the suitable functional framework for these problems. If you have fractional problems, which means non-local problems, then there are these fractional Laplacians. I mean, I'm not been working on this, but I know that there are fractional P Laplacians and also fractional Orlicz Laplacians. So I think that these function spaces are the natural functional framework for these non-local problems. And as I said, there are papers by Ariel Salort and some co-authors who considered, for instance, this kind of problems and also eigenvalue problems in this spirit. So exactly in the sense that you, Pasquale, were have in mind, I think.
Okay, thanks again. There are some other question? If not, thank you again, Andrea. Thank you.
Thank you.